This section deals with organometallic reagents. And organometallic reagents are known for producing carbon nucleophiles. So the key words here are carbon nucleophiles and, of course, organometallic. So let's look at a background for organometallic reagents. So typically from last semester, Organic Chemistry 1, we studied that if we have alcohols, ethers, alkyl halides, so let me just draw an alcohol for you. So suppose I have a methyl attached to an OH, that's an alcohol like methanol, so ROH. This would be ROR. And then alkyl halides are RX, where you have halogens. That in these compounds, the carbon atom is bonded to a more electronegative atom. So oxygen is more electronegative than carbon, and the halogen is more electronegative than carbon. So the carbon atom, therefore, is less electrophilic and reacts with nucleophiles. So if we look at an example here where we have ethyl attached to a halogen, it could be fluoride, it could be chloride, it could be iodide, etc. We notice that the carbon atom, if you recall, has an electronegativity of 2.5. So that's for carbon. For the halogen, it is greater than 2.5. Now, what does that mean? It's beyond math. It means that electrons are being pulled toward the halogen, making the carbon less electron rich, which means it's electron poor, which is electrophilic. So meaning that you're going to get a delta plus on this carbon, more positive, and the X will be more, if this allows me to draw, more negative, delta negative. You learn this in basic chem in terms of bond polarity. So the electrons are being drawn this way. So if you don't recall that, fluorine, for example, has an electronegativity of 4. Just to give you a few examples, Cl has an electronegativity of 3. And bromine has an electronegativity of 2.8. So they're definitely greater than the electronegativity of carbon. So therefore, we say that this carbon right here is an electrophilic carbon. Carbon. So let me put a space here so that you don't think that's 2 C's here. So an electrophilic carbon. And we know that they react, electrophilic carbons, they react with electron-rich nucleophiles. All right, so electrophilic and nucleophilic. So that's what happens when you have an electrophilic carbon. So again, the electrophilic means it's electron poor. That's what it means. Needs more electrons. And therefore, this would act as your electron-rich nucleophile. And the reaction would occur this way. Where X now is replaced with Y. So we learned this in substitution reactions, nucleophilic substitution like SN1, SN2 reaction. So notice that the carbon here was electrophilic electron poor due to the difference in electronegativity. Now, if we have the carbon bonded to an atom that is less electronegative than itself, then the opposite will happen, meaning the carbon now will be nucleophilic, partial negative charge, and it now will interact with an electron poor electrophile. So notice what's happening now. Now imagine you have M, it's a metal. Metals tend to have lower electronegativities, if you remember from Gen Chem. So of course, carbon still has a 2.5 electronegativity, but the metal is actually less than 2.5. And this now, look how the partial charges are going to be reversed. You're going to have delta minus, but delta plus on M. And therefore, this carbon will be an electron-rich carbon, nucleophilic, so what is it going to do now? It's going to react with electron poor electrophiles. So this right here is your electron poor electrophile. So look what's happening now. C is going to be bonded to the electrophile E. So it's going to be, if this allows me to do it, CH three, CH2, E. Plus M plus. So once again, notice how the carbon in this case was the electron rich and was able to attack the electrophile versus being attacked by the nucleophile in the previous case. So this is an important distinction to make, and be sure to understand what I just went through here, and of course, ask questions when we meet. So this is our focus from now on, at least for the rest of this chapter, is we will work with carbon atoms as nucleophiles produced by using organometallic reagents. So let's go now to the next page. And in this one, what we notice is, let's look at some examples of this carbon metal bond. So we say here a carbon bonded to a metal is nucleophilic because most metals are less electronegative than carbon. An organometallic compound is a compound that contains a carbon metal bond. So remember, organic chemistry is about carbon-based compounds, and then metals are metallic, comes from metals, metallic elements. So we look at three major types. The three major types are organolithium, organomagnesium, and organocopper. So lithium, magnesium, and copper. So let's look at the electronegativity. So once again, carbon is still 2.5 as the electronegativity. But if you look up lithium, it's a 1.0. So that gives us a difference, delta En, of 1.5. So 2.5 minus 1 is a 1.5. Carbon magnesium, 2.5. Magnesium is a 1.2. So that gives us a difference of 1.3. And carbon copper, again, 2.5 for carbon. But copper is 1.8. So it's more electronegative than the previous two. And that gives us a difference of 0.7. Okay. You realize that, if you remember from Gen Chem, that the larger the gap between electronegativities, or the difference, the more polar the bond will be. So in this case, I'll use a different color. The carbon-lithium bond is the most polar bond. Because the difference in electronegativities is the greatest. And therefore, that means carbon in the organolithium and the carbon-lithium bond is at an advantage here. The advantage is that this carbon right here will be the most electron rich. Right? So it's kind of like an analogy of like splitting, let's say, an amount of money, right? In this case, let's say carbon can split the money. Let's say $100 can be split into, let's say the carbon gets $75 and then the lithium gets $25. Carbon gets, in this case, in the second one, carbon gets $50, and then magnesium is going to get maybe $50. And then carbon copper will be, let's say, less, 25, I would say, about the same. So or actually, it would be more. Carbon would still get more. So as an analogy, again, carbon is always getting more, but it's getting less as you go from carbon um, to magnesium and carbon to copper. Very well. So these are covalent carbon bonds. So they are covalent carbon metal bonds. To be ionic, the electronegativity difference must be over 1.6. The reactivity of an organometallic compound towards an electrophile depends on the polarity of the carbon metal bond. So all you have to remember is that organolithium are the most reactive. Then the organomagnesium, which are going to be named shortly. And of course, they are more reactive than organocopper. So these would be, organolithium would be the most reactive. And the organocopper would be the least reactive. Of course, they have their uses. So you can't always use organolithium. Too much reactivity isn't always a good scenario. Very well. So how are they prepared? How are organometallic reagents prepared? So we'll talk firstly about organolithium and organomagnesium. Now from now on, we're going to refer to organomagnesium as Grignard reagents. It's a very, very popular name in organic chemistry, Grignard reagent. So that G is silent. Are typically prepared by reaction of an alkyl halide with a corresponding metal. So here's an alkyl halide with lithium, 2 moles of lithium, that produces the organolithium reagent, and of course, an ionic compound salt, LiX. So I'll just give you an example. So I could have bromine like this, and I can react this with lithium. And I'm talking about lithium metal in this case, not lithium ions. So be very careful. So we need 2 moles. And what would happen is the following. You would distribute the lithium. 1 goes to the R group, and 1 goes to X. So the lithium goes, 1 goes with X and 1 goes with the R group. So therefore, you're going to have R lithium, and of course, LiBr. Now, sometimes, generally, this can be left out. It's a byproduct or a side product. This is more of a general chemistry, so it can be left out. For the Grignard reagent, you don't need 2 moles. You need 1 mole of magnesium, and you're using that, you're putting that in ether. So you must use ether, Okay. And what happens here is quite different, is that magnesium, in a sense, inserts itself in between. Okay, so Okay, so it inserts itself between the R and the X. So you get RMGX, carbon, magnesium, and then the halogen. So here's an example. You can have an alkyl bromide. We use magnesium and ether. Once again, this is magnesium metal, not magnesium ion. So there's a difference between them. Ion has a charge. So in this case, what happens is that, again, the magnesium is going to insert itself between the alkyl, the carbon, and in this case, the bromide. And we have a name for this. We call this the Grignard reagent, and that's what I like it to be called. So make sure you remember the name of the magnesium, the organomagnesium. That's called Grignard reagent. And the third type is organocopper reagents. We usually refer to them as cuprates or Gilman reagents. Either one of those is fine. You can even call it organocopper. Are prepared from organolithium reagents by reaction with copper plus copper 1 salt, which is in the form of copper 1 iodide. Now you have to recall, you have to remember that it involves 2 steps. And number 1 is you have to make an organolithium. So this one depends on the organolithium. And then 2 is you have to add copper iodide, copper 1 iodide. So here's an example. This alkyl chloride in this case, we add lithium. Even if we just add 1 mole, we can ignore the byproduct. We will get this one right here, the organolithium. And then if we add copper iodide, we will get both okay, so what's going to happen here is notice that you have 2 R groups, and this is basically your R group. Now you have 2 of them. Here's an R and there's an R group attached to the copper. So it looks a bit weird here, but that's copper, the organocopper. So pay attention to the formula here, R2CuLi, not RCu. So that distinction has to be made. So I'm going to end with this here. A Grignard reagent is in the form of RMGX, where X is equal to Br. So the halogen can be bromide, chlorine, iodine. An organolithium reagent is in the form of RLi. Organocuprate is in the form of R2CuLi, as we just mentioned. Organolithium, Grignard and organolithium reagents react as if they were carbanions. They are not true carbanions because they have covalent carbon-metal bonds. However, we can think of them conceptually as carbanions. So you kind of, you can think of it as we will examine with acetylide anions. So pay attention to acetylide. So if you recall, carbon has an electronegativity of 2.5. We did this last semester. Sorry, I pointed to the wrong one. Well, it's the same. Anyway, it doesn't matter. For carbon is 2.5, and this is a 0.9 for sodium. And it's actually ionic. And the reason why it's ionic is because the difference is greater than 1.6. So in this case, we say delta En is 1.6. So you're taking 2.5 minus 0.9. And it's ionic. So we have CH3, C, and then we have this right here. Okay, where you have the cation and where you have the anion and the cation. So we'll say this is ionic. Now, the reason why we say you can think of them as reacting this way, I'm going to show you here really quick what I mean. So if you look at RMGX, and let's say we have something as simple as CH3, and then we have a CH, and then I have the Mg, and then you have the Br. Okay, so one way of thinking about this, and this always helped me, is if the charge on magnesium is +2, the charge on bromide is -1, and the charge on the carbon, it's a carbanion, is a -1. So you see the charges balancing. So 2 positives and 2 negatives, they cancel out. So you can think of it that this is your nucleophilic carbon. So the carbanion. Now, in reality, we can think of them that way, but in reality, there is a covalent bond. So it would be like this. So remember, we've seen this before, where we now focus on this bond right here. That can be the nuclear, where the nucleophile would attack from, moving those electrons in that bond.